Okay, folks. Let's do this thing. Okay, so you guys can see this okay? So today we're going to talk about scattering. We'll continue our discussion from last time. This was motivated by the Green's function approach because we want to go beyond the Born approximation. And this will lead to the partial wave treatment of scattering. And so that's the plan for today, is to do partial waves. But the whole point of this is the reason we're doing this, the main point is to go beyond the Born approximation. Okay, so let's sort of take up where we left off. And the thing was, we had this new scattering picture, and in this new scattering picture, we have our potential at the center, at the origin. And really what we want to do is just solve the Schrodinger equation. Basically, everything is based on solving the Schrodinger equation, which is just that. So we solve it, and then we get some eigenstates, or we get an eigenstate for a particular energy. So at some energy, E, this is what the eigenstate looks like, just some big, weird, wavy thing. And then here, we see that we can, far away, we can define our J incident, where we're using the fact that J is the probability current, is our old friend from last semester, this weird formula that suddenly has become really important. And we can calculate our probability current way far away just by plugging into that formula. And then we also have some detector, and we can calculate our probability flux into the detector. I'll call that the scattering from J scattering, just by going to the detector and calculating that, plugging into that formula, because we know the psi at the detector. And then we can just plug into the formula and get the J at the detector. And the detector is here, and the detector has some area, ds, which is related very easily to its solid angle, d omega, by r squared d omega. And to get the little vectors right, there's an r hat there, because ds is for a flux integral, it's an area, it's a little vector pointing perpendicular to the area. You learned that somewhere in calculus. And then from all of this, we then see that we can write now the differential cross-section can now be written in this language, and similar to what we did before. But now the probability flux flowing into the detector is J, is the scattering, the J, the probability, this J scattering here, dot ds. That's the probability flux flowing into the detector. And I have this d omega on the bottom. And so this product, or dot product, is dr, is the probability per time that flows into the detector. All right, so that basically tells us what's the probability that the particles will scatter in that direction. Okay, that's the differential cross-section. So using this, and so then the reason why the Green's function treatment was so useful is because from the Green's function, what the Green's function gave us was a solution. Green's function allowed us to solve the Schrodinger equation in some general way, and then it gave us this solution, which is that we see that the general solution of the Schrodinger equation for scattering problem, where energy is greater than 0, is I have an incident wave plus a scattered wave. And the scattered wave gets multiplied by this thing in front, which is the scattering amplitude. And it goes to e to the ikr, that's the scattered wave. And the scattering amplitude is a function of theta and phi, because that's what r hat is. It just points in the direction of theta and phi for the r vector. Okay, and so that's very important because that tells us then that the wave function for a scattered wave always looks like this. I have my scatterer, say some scatterer, and then I have, actually let's draw it like that, and then I have my wave, that's my incident wave, and then I have my scattered wave. And so that's what the wave function always looks like. So that's like a big insight. That's like really important, really useful. It's kind of obvious when someone points it out to you, but it's profound and useful and important and kind of simple too. And so that's the incident momentum. And then this is the scattered wave. And so that's I'll call that the scattered wave. So that's what happens in quantum mechanical scattering. You have an eigenstate that looks like that. And then the Green's function approach was quite nice because it also allowed us to figure out what that scattering amplitude is, f of r, the thing here. We found that we derived a little formula for it. And that's a formula, I'll just say f of theta phi, and we derived a formula for it. Nice formula. And here it is. E to the minus I k r hat dot r prime, v of r prime, psi of r prime, r prime. Okay, and so that's the scattering amplitude. And so in some sense, it looks like we're done. We've solved the scattering problem. We've defined all the different terms and we can calculate them. Because the whole point, remember, is to get the differential cross-section, d sigma d omega. And so to get d sigma d omega, then we want to get d sigma d omega. So now we have to still do a few more steps, but we have 1 over j incident times the scattered j dotted into that ds d omega. And so what we can do now is this is the most important thing that we want to figure out, because that's what tells us what's going to happen in an experiment. The differential cross-section literally tells us how many particles are going to go in our detector, the experimental thing. So that's what we want to, that's the information we want from quantum mechanics. We want to understand that process. So for scattering, so let's use our newfound knowledge to calculate the differential cross-section. And we started that last time, and we see that the J incident is the easiest, that's the easy one, because J incident, we get that's just going to be h bar over 2mi, remember psi star del psi minus psi del psi star. And so we just plug in our psi, and here's our wave function up here, that arrow, and then we go here, and then we just plug it in. But for the J incident, remember we're talking about out here, so R is far away for the J incident, and so for the incident wave, we can ignore the scattered part. We can ignore the scattered part for the incident wave, because the idea is that we're looking, we want to know what the probability flux is far away, say off to the left, far, far away, in which case the incident wave dominates. And so we can plug in psi k of r is approximately equal to e to the I k dot r, or j incident. And then when we plug it in, we get that j incident is, just plug that plane wave into it, and we get that j incident is going to be h bar k over m. So we did it. We did that one before. And so then the magnitude of j incident is very simple. It's just h bar k over m. All right. But now we want to but now we got to do this other term. This is the hard part. That's the hard part. So that's the hard part, but let's do it. So this j is that's the scattered j. So now we see that d sigma d omega is is equal to m over h bar k times j, and now this is the scattered j into the detector dot ds of the detector divided by d omega of the detector. And so now we have to plug in, now we need j scattered into detector, and that's harder because now we can no longer ignore the scattered wave. So what we'll do is we'll use, now we have to use the entire psi is equal to the e to the I k dot r plus f of r hat e to the I k r over r. And then we have to plug into the formula for j. This formula up here. I don't want to write it again. Okay, so let's do that. So when we do that, the first thing that we have to do is calculate the gradient. Because see, we have a gradient here. That's the first thing we have to calculate, is the gradient of psi. And so let's do that. So gradient of e to the I k dot r plus f of r hat e to the I k r over r. All right, so we do that, and what we get is the gradient when it hits that plane wave. Do you guys know what the gradient gives us when it hits a plane wave? Can you tell me now? I'm asking you a question. This is why we like plane waves, because the math is simple. What happens when the gradient hits that plane wave?
Is it just ik times, oh, sorry.
No, go ahead.
That's right. It's just ik times the plane wave. So that we like. But then we have to hit this guy, and that's more messy because it's a big mess. I mean, we're doing this in spherical coordinates, and so we have to use the spherical gradient, and you know, it's a big, complicated formula. But it turns out that we can simplify it because it has, you know, it has, the gradient has r hat term, theta hat, and phi hat. It has 3 terms for the gradient, and it's some complicated formula. I don't feel like writing. You guys dealt with it last semester. And one term gives you a component in the r hat direction, one gives you a term in the theta hat, and the other in the phi hat. And I just want you to notice that what we're talking about is flux going into the detector. Now here you see the detector. Now notice that the detector is this. And so the detector, when you dot the flux into the detector, the area ds is proportional to r hat. Okay, so what that means is we only care about the flux going in the r hat direction, because other flux, if the flux is going in, for example, this is that's the theta hat direction, and the phi hat direction is like into the board page, whatever, and that's the phi hat direction. So the point is that those directions are perpendicular to r hat. So flux that's flowing in the theta hat direction or the phi hat direction does not go into the detector. Do you see that? That's like swirly flux. It's not going into the detector, so we can ignore it. So that's kind of nice. So these terms we ignore. We ignore the theta hat and phi hat terms. So that's really nice. So that means we only worry about the radial component of the gradient. And that part is easy. Radial components are easy because notice that this depends on theta and phi. And so the radial component flows right through that. And so then we see that what we have then is that the gradient becomes very simple. It's just r hat times f of r hat, because that's just a constant for the derivative. And then there's a radial derivative, ddr. And now we have to take the radial derivative of e to the ikr over r. Okay, so that's the gradient. It's nice, because we ignored those guys. And so, but now we still have to take we still have to do the quotient rule, calculus, quotient rule. So we got to do that. So we see then that what we have is I k e to the I k dot r plus f of r hat e to the I k r times I k r minus 1 over r squared. So I'm just doing the quotient rule in calculus. Okay, times r hat. Okay, and so now if we put it all together, okay, so that's the gradient. But now what we're going to do is do a bunch of algebra, because I gotta do, it's tedious algebra. I'm not going to do it all for you right now, but remember, we got to calculate this h bar over 2mi psi star del psi minus psi del psi star. So we're literally doing this where psi is equal to e to the I kr plus plus f of r hat e to the I kr over r. So we're plugging that into there. And when we do the bunch of algebra, we see that we get j. We're going to get that j. It's actually this, I'll call it the scattered j, is equal to h bar over 2mi times, and when we just look at the scattered part, we're going to get a bunch of stuff times e to the I k dot r hat plus 2ik over r squared f of r hat squared times r hat. Okay, so there'll also be another term somewhere. There'll also be another term where there's another term in there that we ignored. If you do the algebra yourself, well, maybe I should write this other term in there just for completeness. There is one more term when you do the algebra. You'll see there'll be a term plus 2ik, but this is just that's just going to be the incident flux. So when you actually calculate the flux at the detector, there'll be the incident flux plus the scattered flux. And that's the scattered flux. And for our differential cross-section term, we only care about the scattered flux, what occurs due to the scattering. So that's this part that I've underlined right here. So this part we don't need to worry about that part. So what we have to do then is we have this scattered flux, and we have to look at the scattered flux going into the detector. And I have two terms, and I'll call this term 1. Oops. I'll call this term 1. I'll call this term 2. Now let's consider term 1. And it turns out that that part, the r hat does dot into the flux, and so we have this, we have our detector, which is here at the location r, and we see that that's an r hat, and the detector also we see that ds is proportional to r hat, so the dot product works, so we can't just ignore that term. But it turns out that this first term goes to 0, and the reason it goes to 0 is notice that it's a plane wave, and this is the direction of k. It's the incident direction in this way we've set up the problem. And so this is a plane wave, the first term, and so let's draw a plane wave. A plane wave looks like this. So this is slightly subtle, but it's not that subtle when someone points it out to you. And so when that plane wave, and notice that what's happening in a plane wave is, a plane wave looks like this. We have a plus part, a minus, plus, minus, plus, minus. So what's happening is we have these parts of the wave, plus, minus, plus, minus, plus, minus. So the detector is kind of big, and these quantum waves are little, and so there's going to be a bunch of plus minus that hits. So when we do the flux integral and actually calculate the flux, we're going to end up integrating all this plus minus. And what do you think it adds up to? Someone tell me. What do you think it adds up to? What?
0.
Right, because it all cancels. So when we calculate the flux from that term that goes into our detector, it adds up to 0 because our detector is here at this angle, as I just drew. And so then,
Professor?
Yeah.
When do you do the flux integral?
Well, because the whole point is that we're trying to figure out this. Where am I? Here, yeah. Okay, so here's the differential cross section. And so it's right here. So that's the term we're talking about. It's the flux. So that's because we're trying to figure out how much probability flux goes into our detector. And that's what this term is. Oops, that's not a vector. And so the quantity we care about is the flux that goes into our detector. And so the flux from that term is going to add up to 0. Does that make sense?
Is that but in that equation it's just J scattering.
Yeah.
But when do you take the integral of that?
Well, you can think of it as you can think of it as just what is. You can ask yourself, what is the differential cross section? What is the amount of particles that's going to go into my detector? And that's what we're ultimately trying to figure out. And so then, as you calculate the number of particles, there's always going to be some. There's always going to be some integral, because in the end, like for example, we have this. Let's see if I can remember. dN is equal to luminosity times d sigma. And so then I could divide this by delta omega, because I can see how many particles go into my detector. And I multiply by delta omega. And so the number of particles per time into my detector dN is L, the luminosity, times d sigma delta omega. So that's the differential cross section. But then there's this delta omega. So that is the integral, because then the number of particles is the integral of dn is equal to the integral of this. I'm just saying there's always going to end up being some integral somewhere. So now we're integrating that to figure out how many particles are really going into my detector. And so the point is that there always will be some flux integral.
Oh, okay, so that's when we are later figuring out the number of particles.
Yeah, because that's
Okay.
sort of the whole point of the whole formalism, is to figure out how many particles are going into my detector. And so the point is that term number one, when I try to figure out the flux from that term, it's going to integrate to 0 across my detector. So we can ignore it.
Yeah, okay. Is that also true when we try to find the cross-section, sigma? We also integrate it over d omega, but that's...
Yeah, that also is true, because for the total cross-section, you're basically saying how many, if my detector covered all solid angle, what would be the amount?
Okay. Is that enough? Just over omega is enough, or do we have to integrate it over the surface ds as well in order to get the that term one to be the integral?
Well, when we calculate the total cross section, we integrate over solid angle, because that's the definition of total cross section. But what we're doing now is we're trying to define the differential cross section, and to define the differential cross section, we're actually doing a flux. We're doing the flux. So we're doing this. We're treating it at the level of probability flux in order to derive the differential cross section, where I'm pointing my arrow. But once we've derived the differential cross section, then we can forget about this flux treatment, and then we'll just use the formula for differential cross section, and then we can just worry about solid angle. So we're sort of getting into the details of flux in order to derive the differential cross section. But once you have the differential cross section, you only need to worry about solid angle. Does that make sense?
Okay.
All right, so now what we have to do is we're going to deal with the second term. That's the one that matters. Okay, the second term matters. So now let's do the second term. And so for the second term, we're going to take now this term, and we're going to dot that into our expression for the differential cross section. So this is our expression for the I'll put some stars here. So we got to dot that term into ds for the detector. So we'll dot that. So now we have to look at the second term. And so we have to calculate now J scatter dot ds for the second term. And so we're going to take this formula, and it's for the second term, it's h bar over 2mi, that part. And then the second term here, you can see it up there. I'm going to rewrite it here. It's 2ik over r squared times f of r hat squared times r hat dot ds. But then you notice that ds for the detector is, remember that, this is the geometry, and the detector is here that covers some solid angle, but ds is equal to r squared d omega r hat, because that's the direction of ds. So that's r. So then we can replace ds with r squared d omega r hat. And so now it's really nice, because something really nice happens, because you see I have r hat dot r hat equals 1. Yay. And so then this expression becomes really nice. And you see the i's cancel, and everything cancels, and you get h bar k over m times f of r hat squared d omega. And so that's a really beautiful, simple expression, because now we can just plug that in. Because remember, our expression for the differential cross-section was d sigma d omega is equal to 1 over j scattering, or I'm sorry, that was the incident, times j scattering dot d omega. I'm sorry, I keep missing these little factors, divided by d omega. And so this, and then this, remember, was h bar k over m. So we basically have 1 over h bar k over m times 1 over d omega times this j scattering dot ds, which is h bar k over m times f of r hat squared d omega. And notice everything cancels. That cancels that, that cancels that. And we get this amazing answer. D sigma d omega is equal to f of r hat squared. Ta-da! I love that. That's why. So all that complicated stuff, we did all that complicated stuff to get this really simple answer, and it's really quite beautiful and elegant, and it gives you a lot of physical insight. And that's why it's sort of worth going through all those details of the algebra, because you end up with this really profound, beautiful, simple answer. And in fact, you can just forget about all that algebra and just focus on the answer, because the answer is the most important thing. Because what this is telling us is that if you solve the Schrodinger equation, and this is really a profound insight, if you solve the Schrodinger equation, there it is for some scatterer, then you're going to get this wave function, an incident wave and an outgoing wave, where that's the incident, and then this is the scattered wave. And the functional form is really simple. It's just psi is equal to an incident wave k dot r plus some scattering amplitude f of r hat times e to the I k r over r. And the beautiful insight is that this part of the wave function is exactly equal to the differential cross-section, the experimental quantity, the quantity that we really care as an experimentalist. That tells us how many particles go into a certain angle. That tells us the probability to scatter into a certain angle, because f of r hat, f of r hat is a function of theta and phi. And so we see then that the differential cross-section is just f of r hat squared. So this part of the wave function is the differential cross-section, or the square root of it. You just got to square it, right? So that's pretty cool. And so that really shows you that this form of the wave function is really important. And that was why we went through all that trouble with the Green's function stuff, was to derive that form of the wave function. So now you can see that all that math was for a reason, but the results are simple, because this little formula is simple. That guy who gets 2 stars is simple, and this guy who gets 3 stars is simple. These are simple little formulas that are easy to have a lot of physical insight. But the part that's not so simple is when we start asking ourselves, how do we get this scattering amplitude? Because we still have this little problem. How do we get that thing? How do we get that scattering amplitude? And so let's take a look at this for a moment. And so what we do is, remember from the Green's function treatment, we had that f of k of r hat, from the Green's treatment. Let's see, I'll just erase that. We derived this expression using the Green's function as this complicated thing, negative m over 2 pi h bar squared e to the negative I k r hat dot r prime times v of r prime times psi of k r prime d cubed r prime. Okay, now it turns out that there is one way that we can get this, because now we have a form for psi. And so what we can do is we can take this and we can plug it into there. And then we can try to do that integral. Now, you can see pretty immediately that that's a fairly bogus thing to do, because I see that the scattering amplitude is actually in the psi. But what we can do is we can say, we can make an approximation. And we can say, suppose we have weak scattering, in which case, when we plug in the psi in, we'll plug it in, we'll say that psi will ignore the scattering. We'll say, oh, the scattering is weak. And so when we plug the psi in, we'll say that psi is approximately equal to e to the I k dot r, a plane wave. And we'll just ignore all that spherically symmetric scattered wave stuff. And that's the weak scattering approximation. And then when you do that, then what happens is what you get is you plug that in and do the math. So plug in, do math, play with it, and what you'll find is you get the Born approximation. And I'm not going to do the math. It's actually pretty easy. It's not fancy. The insight, oh, oops, Born math. You get the Born approximation. And to get the Born approximation, the insight is that you have to realize that the K in our new formalism is what we call Ki in the old. And the what we call Kr hat in the new formalism is what we called Kf. So this is the new formalism, and this is the old Born approximation treatment. You have to recognize that. And that is like, you have to think about it a little bit. So that's a homework problem. I want you guys to mess around with that, and you get the Born approximation. And the Born approximation is just going to be, you're going to find once you go through the math that you're going to get d sigma d omega is equal to m squared over 4 pi squared h part of the fourth this is going to be the k final, v k initial, and that's the Born approximation. You're going to get that. So derive that. But now you can derive it using this new technique. And so you might say to yourself, well, okay, that's nice, but we wanted to go beyond the Born approximation. So first, I just want to say that even though we get the same answer as the Born approximation after doing all this fancy math, we still have some new insights, because the new insight that we got is that we now understand the form of the wave function is this incident wave plus the scattered wave. So that was something we did not understand before, but now we understand it. And we understand that this is the differential cross-section, or the square root of it. Okay, so that's some insight, but still we want more insight. So we still want to go, so how do we go beyond the Born approximation? How do we go beyond Born? Okay, what we want is a Born supremacy. I've been watching the Born Identity series lately, so I'm really thinking about Born a lot. Okay, so we want to go beyond Born. We want Born supremacy. So what we got to do then is we got to be a little tricky. So to go beyond Born, what we have to use is the partial wave analysis. And this allows us to go beyond Born, okay? So now let's do the partial wave analysis. All right, here we go, partial wave analysis. And this is how we go beyond the Born approximation. Born approximation. Okay, the partial wave analysis is really weird. And when you first see it, it's really, I found it really confusing as an undergraduate when I learned it. In fact, I don't think I did learn it as an undergraduate. I think I learned it in graduate school. Can't remember when exactly I learned it, but I do know that when I first looked at it, it was really weird and confusing. But now, you know, after staring at it for like 30 years, it's not quite so confusing to me anymore. But it is kind of weird. And so, but it's very cool. It's very cool, and it's a very, in my opinion, sort of the most powerful and profound way to think about scattering, at least in my world. You know, I'm not a high energy theorist, you know, I'm sorry, high energy physicist, I'm a condensed matter physicist. And so in my world of condensed matter, in terms of actual scattering processes that occur in crystals and nanostructures and little objects, this, in my opinion, is the most powerful way to think about scattering. So I really like it a lot, and use it actually a lot. But it's kind of weird when you first see it. So it is all based on this concept that we derived using Green's functions, which is that the solution of the Schrodinger equation for energy greater than 0 for a scattering process off of some potential, where we have some potential, is this. We have a incident wave plus a scattered wave. And the scattered wave is modulated by some function of theta and phi times an outgoing wave, e/kr over r. Okay, so if I draw that eigenstate graphically, then it looks like this. I have an incoming wave, and I have my outgoing wave, and that's what it is. Okay, but what we're going to do the partial wave analysis, this is the trick. It's a math trick. It's a change of basis. So we're going to do a change of basis. And what we do is we want to change our basis into the angular momentum basis, L basis. And basically this is this is a basis state, because you know that this is a basis state because this is a solution of the Schrodinger equation. And so you know that the solution of the Schrodinger equation always gives you a complete set of orthonormal eigenstates, because it's the eigenstate of a Hermitian operator, which always gives us a complete set. So we know that these are basis states. But what I want to do is now, so this is a type of basis state, but notice that it has no rotational symmetry. Because I got that rotational part, the scattered wave, but I also got that incident wave. And the incident wave has no rotational symmetry. The plane wave has no rotational symmetry. I can't, like, if I tilt myself, then, you know, I can't like tilt the plane. If I tilt the plane wave, then it looks different. If I rotate it, then it's totally different. I think that is sort of intuitively clear. Oops. And so it has no rotational symmetry. So what we got to do is we got to take this eigenstate, which is, you know, this one right here, and we're got to write it in terms of new functions that have spherical symmetry, and that's why I say the L basis, spherically symmetric. We have to write it in terms of a spherically symmetric basis, and the spherically symmetric basis is the set of angular momentum eigenstates that equals 0 to infinity. So let's take all the angular momentum eigenstates, which have spherical symmetry. They're rotationally symmetric, and then let's write this. Let's decompose this eigenstate, the one that we've derived, and we're going to write it in a new way. We're going to write it in terms of a sum of rotationally symmetric incoming waves plus rotationally symmetric outgoing waves. And that's what we're going to do mathematically. So before I dive into the math, I want to tell you what we're going to do. So intuitively, this is what we're going to do. But we're going to do a bunch of equations, right? So don't worry, the equations will soon come, and we will derive it precisely and exactly. But it's easy to get lost in the derivation and to lose sight of what we're even doing because there's so much math. So this is what we're doing. But there's a trick, which is that these are the incoming waves, and these are the outgoing. But there's a trick, and this is the crucial trick. The crucial trick is that the outgoing waves are phase shifted. They're phase shifted. And it turns out that this phase shift is the most important thing. Who would have thought that? And when you first see this, it's just like, what? Because it's not obvious at all that the phase shift would be the most important thing. But it turns out that you can write your scattering amplitude, f of theta phi, is equal to some weird function of the phase shifts. And remember that d sigma d omega, which is experimentally the most important thing, is the scattering amplitude squared. So that means that I can write the differential cross section as some weird function. I haven't told you what that function is yet, but it's going to be some weird function of these phase shifts. And that's why the phase shifts are the most important thing. And the phase shifts completely characterize the scattering process. And it's a sum over all these, it's this weird angular momentum sum. And so this is a very sort of new and weird way to think about scattering if you've never seen it before. So I appreciate that it's really weird, but it's really powerful and it's really useful. And so it's worth learning. But you know, your mind rebels at new things. I mean, that's how everybody is. Okay, so let's try to understand this. Okay, so this is our strategy. This is the partial wave analysis. It's to basically figure out what are these phase shifts. So we have to understand this concept of phase shifts. And what am I even talking about? Okay. So these phase shifts are super important. And so it's just really weird, you know, why they would be important, but they really are. And so let's try to understand that. Okay. So to understand that, a good place is to remind ourselves of the free particle. So let's consider a free particle, eigenstate. And there are different bases for the eigenstate. Because the eigenstate is this, I mean, it's a solution of H psi equals E psi. And for the free particle, there are different ways to solve this. Like we could solve it, when I say different bases, what I mean is we could solve it in Cartesian. And then we can get psi is equal to, can someone tell me what the eigenstate is for a free particle in Cartesian coordinates? You've all done it. You've all solved it. What is the eigenstate for a free particle in quantum mechanics in Cartesian coordinates? Well, maybe I should say, what is the eigenstate of a, yeah?
It's like e to the I px.
Yeah, but in 3 dimensions, you just doing, what is it in 3 dimensions?
Oh, well, in 3 dimensions, it would just be like a dot product in the, like, you know, exponential.
Exactly, e to the I k dot r, a plane wave. Okay, and I know you've all, you know, now you're all like going, oh yeah, because you all know that. All right, but you could also do it in spherical coordinates. And then psi is something different. Does anybody remember what it is in spherical coordinates? If you just solve, you know, this is it, the Schrodinger equation. And you all did this, but you might not remember because it's, you know, it's not like totally easy to remember. But does anyone remember what is the eigenstate of a free particle in spherical coordinates after you know, grind through the Schrodinger equation in spherical coordinates. You guys remember? Okay, that's fine. I just want to see. It's a Bessel function. It's this, J sub L of KR. And it has it has well-defined angular momentum. Angular momentum equals L, and K is the energy, because remember K is equal to square root of 2me over h bar. So when I say K, I'm referring really to the energy, because it has no sort of direction. It's spherically, it has a rotational symmetry, but it has a well-defined angular momentum, the eigenstate psi. Well, it's actually a little bit, I guess I should write it, it's actually times YLM theta phi. Okay, so that's the eigenstate. It's a Bessel function times a spherical harmonic. So that is your free particle eigenstate for a rotational symmetric system. And so what we do is, you guys remember that let's consider the spherical case, because you did this last semester, but you're probably a little rusty on it. Spherical spherical coordinates. Let's solve the Schrodinger equation in spherical coordinates. All right, so let's do that. And so when we do that, what we have is we have H psi equals E psi. That's what we're solving. And so where H is equal to kinetic energy plus potential energy. And when you solve it, and E is greater than 0, and when you solve that, which you did last semester, what you find is that you have the eigenstate has quantum numbers of energy, and then this is L, angular momentum, and then this is M, that's the Z component of the angular momentum. And so then when you write the eigenstate, it has a radial component that depends on energy in L, and it has then the spherical harmonic, which depends on theta and phi. Okay, so that should look familiar. So that is the generic solution for the situation when you have a potential that depends only on the radial coordinate. Okay, so it's a spherically symmetric potential. And so then what we have is the spherical harmonics are easy. You know them, they're written in a book. The hard part is to get the radial part. And to get the radial part, you have to solve this equation, negative h bar squared over 2m, 1 over r squared ddr, r squared ddr, plus v of r plus h bar squared l times l plus 1 over 2m r squared rel is equal to e rel. Okay, does this look a little familiar? This is the radial Schrodinger equation. So you have to solve this this equation to get the radial component of the wave function. And so this should all look familiar because you did all this many times last semester for the free particle, and you did it for the hydrogen atom. And then if you set for the free particle for the free particle, then V of R is equal to what? Tell me, what's V of R for a free particle?
It's 0, right?
Yep, exactly. So for the free particle, V of R is 0 in this equation. And then this equation turns into the Bessel equation. Then this becomes the Bessel equation, a famous differential equation. And you would know that if you took partial differential equations. And so I suggest that all of you take partial differential equations. They're a very useful course if you're going on in physics and you want to do this kind of stuff. And so then if you solve that Bessel equation, then you see then that the solution of this equation is tell me, for the free particle, the radial Schrodinger equation is the Bessel equation, and the solution of the Bessel equation is the what? It's right there. It's on the page. What is the solution? It's almost a trick question. What kind of function is the solution of the Bessel equation?
A Bessel function.
Yay, Bessel function. That's right. That's where they come from. They're the solution to this equation. And and here they are. Okay, so that's where it comes from. And you saw it, it was, I already sort of alluded to it up here, right? For the free particle. And so then the Bessel function is this. You have the radial part, which is a Bessel function for the free particle. We're talking about a free particle. And this is what it looks like as a function of R. It goes, woo. And you've all seen it before. You've all seen Bessel functions before. They're big and they wiggle and they get smaller. And then for the Bessel function, it has well-defined angular momentum because we're solving everything in spherical coordinates, in which case the solution to the Schrodinger equation has well-defined angular momentum, because remember, the solution of the Schrodinger equation is equal to the radial part times the spherical harmonic. And so the radial part sort of is associated with the part that has an associated angular momentum with it, a well-defined angular momentum. That's this, the angular momentum. So this is review. I'm kind of reminding you, what you learned last semester. But now we're sort of diving into the details a little bit more, because now I want you to, what's important now is we have to consider the asymptotic solution. So where R is big. And the reason why we're looking at the asymptotic solution is because, here's our potential V of R, but we have our scatterer here. I'm sorry, our detector. And the whole point is to figure out and the detector is at R. The whole point is to understand what happens at the detector. And the detector, remember, is pretty far away. So all this stuff, so when we're talking about scattering, we're always asking ourselves, what happens far away from the scattering event? At the detector, that's what we care about. And so at the detector, R is big. And so then it makes sense to look at the asymptotic solution of the wave function. And so the asymptotic solution for big R is this, the limit, of big R for the Bessel function is this. It turns out that the Bessel function, as you go really far away, it's just, here's really far away, it's just a sine wave. It's just a sine wave, sine of kr minus L pi over 2 over r. So it's just a decaying sine wave. And that's why Bessel functions are actually really easy. So don't feel afraid of the Bessel function, because it's pretty simple. It's just a sine wave, 1 over r times a sine wave. And it has this weird little minus L pi over 2 in it, which actually makes sense when you think hard about it. And so I will also mention that when you solve this solution of this equation, you know, for the free particle, we get the Bessel function. And something that I did not mention, I just sort of glossed over it, is because it turns out there are two solutions to that. One is the Bessel function, but it turns out there's also another solution, the Neumann function. Now, for a free particle, we ignored the Neumann function because I will mention, let's see, yeah, let's also do small r, limit r goes to 0 of j sub L of kr. And this is just something you can look up in a book, is proportional to kr to the L, which is well defined at 0 because it just goes to 0 at 0. But it turns out that there's another, if you look at this other function, the Neumann function, then the limit of the Neumann function as r goes big. Now the Neumann function is, it's really, it's a very sensible thing, because the Neumann function of kr is equal to, well, I'll just ask you, can you guess? Can anyone guess? It's just sort of like, you know, there's a differential equation, the wave equation, that always has two solutions, sine and cosine. And the Bessel function is kind of like a wave equation. It's just like a slightly more complicated wave equation in spherical coordinates. It's like a spherical wave equation, and it has two solutions, j and the Bessel function and the Neumann function. And asymptotically, the Bessel function is the sine wave, and so that means that the Neumann function asymptotically is what? That's my question. Can you guess? Now, the normal Cartesian wave equation has two solutions, sine and, yes, exactly. So that's why it sort of makes sense that there should be a Neumann term, because it's just the second solution. And so it's also just the same thing. Oh, oops, I missed a k here. K. Cosine kr minus L pi over 2 over kr. So when you think of the Neumann function, you should think of it as just the cosine analog. I got a sine, I got a cosine, which makes sense because wave equation always can be solved by either sine or cosine. Okay, or if we do exponents, it's like e to the ikx or e to the minus ikx. So there's always two solutions, but there's just different ways to do it, different bases. But the problem with the Neumann function is that when we take the limit as r goes to 0 for the Neumann function, it has a nasty little problem. It turns out that it goes as 1 over kr to the L plus 1. So what that means then is that you see that the Neumann function diverges at the origin. And so if your solution does not include the origin, then you have to worry about the Neumann function. But if you're talking about a region of space that includes the origin, then you cannot use the Neumann function because it diverges, and so it does not solve the boundary conditions. Then the boundary conditions is that you should not diverge. So for the free particle, we ignore the Neumann function. We cross it out. because it diverges at the origin, diverges at origin. And for a free particle is free to go to the origin. So the free particle includes the origin. So they cannot have the Neumann function. But the reason why I'm going on and on about the Neumann function is that we will use it later on. Okay, that's why I'm mentioning it. So now let's now let's notice. But for this treatment, we're really concerned now at this point with the asymptotic solution. What's happening far away from the scatterer? And the reason I'm going on and on about this is that it's really the phase shift that we care about. Okay, so we want to understand the phase shift. So okay, so let's do this to understand what's going on. Let's take a closer look at the Bessel function, and let's notice that. And now I'm just going to talk about, you know, the large R limit. And so we know that the Bessel function now, I want to just think of the Bessel function as, which is the free particle solution, as in the large R limit, it's sine kr minus L pi over 2 over kr. But now I just want to decompose that into, I'm gonna write that. Well, actually, it's actually more general. So maybe let's just, let me write it like this. So let's just, it just turns out that there's another way, there's another set of functions that we can use. Instead of, if we're solving the Bessel function, we could also have solved it in terms of these functions called Hankel functions. So this is just another set of special functions. Hankel functions. And this could really confuse you, you know, if you've never seen this stuff before, but it's actually not confusing, because remember I said that all this stuff has an analog to the simple Cartesian wave equation. The Bessel function is kind of like the sine function. The cosine function that is kind of the Neumann function is kind of like the cosine function, you know, with a few little added details that let's not get all caught up in. And then you guys know that when you talk about the wave equation, there's really three functions that you care about. There's the sine, there's the cosine, and what's the third one? We're talking about solution of the wave equation. You have sine waves, cosine waves, and what's the third wave?
E to the power of I.
Exactly, e to the ikx, that's right. Complex waves, right? E to the ikx. And so the Hankel functions are the ones that represent the e to the ikx, okay? So that's why there's really three. You know, there's the Bessel, the Neumann, the Hankel. But don't be confused by that, because it's really just the analog of the sine, the cosine, and the e to the ikx, okay? So the Hankel function is like the e to the ikx. And because now, if I talk about the limit of large R, then at large R, what I'm going to find is that the Hankel function is equal to e to the I kr minus L pi over 2 over I kr. So you see, it's just an exponent, but it has a few added little things. You know, there's a little minus L pi over 2 in the exponent, there's a little ikr on the bottom, but don't get caught up in those little details. Just remember, it's just an exponent, and this is an outgoing wave. Now, remember I said this before, like I'm using these terms, incoming wave, outgoing wave, and that when I use those terms, it makes it seem as though there's a time dependence to the wave motion, like the waves are moving, but there is no time here. But the point is that when I use, and I told you this before, but I'll just remind you, to think of it like as moving, you just multiply it times e to the minus I e t over h bar, because that is the time dependence for an eigenstate, time dependence for an energy eigenstate, the eigenstate of the Hamiltonian. So if I was to take that Hankel function and multiply it by e to the minus I e t over h bar, you can see immediately it is literally an outgoing wave. It's moving outwards. So when I say it's incoming or outgoing, I'm serious. You know, I'm not just messing with you. Okay, and so that means then, so now you can see immediately how now it makes sense that the Bessel function is equal to the Hankel function plus the h star, because you guys remember that it's just like, you know, sine x is equal to 1 over 2i e to the ikx minus e to the minus ikx. Now that's a formula that you all know. And so when I say that the Bessel function is equal to the Hankel function plus its complex conjugate, you should just be thinking, oh, that's exactly just like sine x equals e to the ikx minus e to the minus ikx. All right, it's the same thing. Okay, so what we can do then is we're now finally ready to understand phase shifts. So let's talk about phase shifts. And the concept of phase shift is really simple, because now we're just talking about solutions to the Schrodinger equation. And so for the free particle, and psi is equal to r times y. You know, this is the radial part, the radial equation, and that's the spherical part. And we'll just ignore the spherical part because that's trivial. It's just multiplying by spherical harmonic. So this is the radial wave function for a particle is this. That's the radial wave function for a free particle. Okay, that's the wave function, right? And we can see that J sub L is equal to the little formula. Well, I won't worry about it. Okay, and then now let's do something. Let's turn on a potential. So I'm going to turn on a potential. So I'm going to turn on just this potential, where this is minus V naught. Okay, and so this is my V of R. Okay, just a square potential. Okay, I turned on a square potential. So this is my potential. I just turned it on a little, and it's a sucking potential, right? It's attractive, pulls you in, right? It's negative. So I turned on this attractive potential. So now let's turn on this attractive potential. And what does it do to the wave function? That's my question to you. What does it do? Well, how about let's simplify that equation, that question. What does it do out here? And out here, V of R equals 0 in this region. What does the potential do to the wave function in that region? What effect does it have on the wavelength? What effect does it have on the wavelength?
No effect.
Say it again, what?
There's no effect.
Exactly. Because we know that K is square root of 2m e minus V naught, right? Over h bar. You guys remember that, you know, like it's like the K is determined by the kinetic energy. And if the kinetic energy is, if there's no potential, then the kinetic energy is just the total energy. So there's no change. But what does it do to the wave, to the k vector, to the wavelength in this region? Okay. I'll call this region 1, and I'll call this region 2. What happens to the wavelength in region 2? Tell me. And this is all for positive energy, remember? Positive energy. What does the wavelength do in region 1? And you know the answer. You did this in great detail last semester. What happens to the wavelength of a particle as it travels through a region that has very strong negative potential? What does the wavelength do? You know the answer. Can anyone guess? Well, I'll give you two choices. The wavelength either gets longer or shorter. Which? Which one? Come on.
Does it get shorter?
What?
Shorter?
That's right. It gets shorter. And the way to think about it is that it's like it has more energy, right? That's like because you guys know that the kinetic energy, it's like this, like if I have energy here, and if my potential is like this, then you know that in this region of space, I have long wavelength, and in this region of space, I have a short wavelength. Because the kinetic energy is this distance, yeah? Where this is, V of R. And I know you've all done this, so this should be reminding you, you should be going, oh yeah, okay. And that's just what this little formula is telling us, okay? So the wavelength gets shorter in that attractive potential region. So that means it does like this. And so now let's continue to see what the wave function does. And so this is with the potential, and is the dashed line. So this is with V of R not equal to 0. So so the wavelength in region 2, nothing happens. But in region 1, the wavelength got shorter. But now the wave function, is continuous. It has to be. You learned that last semester. It's continuous. And so what that means is, what happens to the wave function far away from the potential when I turn on the potential? What did the potential do to the wave function? Look at it, far away. And the potential did not change the wavelength far away. The potential did do nothing to the wavelength. But notice when you look at the dashed line that I drew and the solid line, they are different. How are they different? What is the difference between those two?
Phase shift?
Yes, it's phase shifted. So I have just proven to you that the most important thing a potential can do is to phase shift the wave function. That's it. This is right here on the page. That's all you need to know. I mean, it doesn't really get any deeper than that. So there's a phase shift. So if I look far away from the potential, the total effect of the potential was simply to phase shift the wave function. The potential induces a phase shift, and this is it. And so here are the phase, and so in this case, the phase shift, I sucked it in. And so that means that the phase shift is positive. So J sub L, and that's just a mathematical thing. Work it out on your own, to yourself. So, and so for this case, delta L is positive. So attractive potential, the phase shift is positive. But if I had a repulsive potential, I would have pushed it out. And in that case, the phase shift would have been what? Tell me. Would it have been positive? for a sucking in, I have a positive phase shift. It's this formula. But for a repulsive potential, the phase shift is, can you guess? Is it positive or negative?
It's negative.
Yeah, because I pushed out. And that's the point of phase shifts. And then, but then there's a nice little, but let's just do it mathematically. So let's just see it mathematically. I just want to show you this little mathematical part, because that will set us up for the next thing, because now you've done it intuitively. Let's do it mathematically. So for v equals 0, then we see that the radial wave function is equal to a Bessel function. But now if the potential is not 0, then we see that now what happens is the radial wave function is equal to a Bessel function that's been phase shifted. I just proved that to you with my little diagram. But let's take a closer look at this, because now let's do some cute little math. Because what I can do is I can say that this is equivalent to, e to the I delta L j sub L kr plus delta L. So I can write that because I can always add a phase shift to the wave function. So I can write the wave function for v not equal to 0. I can write it as e to the I delta L times j sub L of kr plus delta L. This makes the math easier, even though it looks a little harder, but it's just a little mathematical trick. But then what I can do is I can then write this as e to the I delta L, and now I'm going to use the fact that this is the same as sine kr minus L pi over 2 over kr, and then I'm going to decompose the sine wave into exponentials, and so I can write this, that Bessel function, in terms of 1/2. And I'm going to write it in this special way, and you guys can work this out on your own. It's really easy, the math. I just want to show it to you. Kr minus L pi over 2 over minus I kr plus e to the I kr. Oh shoot, I forgot something. Plus delta L kr minus L pi over 2 plus delta L over I kr. So I'm just expanding the Bessel function out, but then I can see that this is equivalent to kr is equal to e to the I delta L times, you can then see that this is equivalent to, this guy is H star. It's the Hankel function complex conjugate, and this guy is going to end up being this guy is going to end up being e to the, once you multiply by that prefactor in front, you're going to end, this guy's going to end up being e to the 2I delta L H sub L of kr. So I'm going to see then that I'm going to get, when I do all of this, then what we're going to get is that the radial wave function is equal to 1/2 times H star kr plus e to the 2I delta L H sub L of kr. And so this is the big result, because and this is just the same as this, It's just a rewriting of the Bessel function, but it's convenient for what comes next, which we'll do next time. But I just want to say that this is an incoming wave, and this is an outgoing wave. And that's a phase shifted outgoing wave, phase shifted outgoing wave. So I took my Bessel function, which is really a standing wave, because remember a sine wave is a standing wave, and I broke it apart into the two exponentials, because a standing wave is like a right going wave plus a left going wave. So you're used to that, sine of x equals e to the ikx minus e to the minus ikx, a right moving wave and a left moving wave. But now I'm doing the same thing in spherical coordinates, but now I have the Bessel function is a standing wave, which is an incoming wave plus an outgoing wave. So it's a standing wave. Standing wave. But there's one nuance, which is that the outgoing wave is phase shifted by the potential. Phase shifted by potential. And what we'll do next is we'll show how that's really useful for figuring out the differential cross-section. That's what we'll do next. Okay, bye-bye.
Thank you, bye.
Okay, bye-bye.
Professor, may I ask you a quick question?
Sure.
Like when you first express the Bessel solution with Hankel's function,
Yeah.
go up. I
Right
thought,
here.
yes. So would there be a minus sign between the two Hankel functions, since you need a minus sign between two complex function to get the sine function?
No, because check it out. Look here at the Hankel function definition. See how there's an I in the denominator?
Okay.
That takes care of it. Haha, see, that's the trick.
Okay, I see. Okay, thank you.
Okay,
Thank you, bye.
bye-bye.
Could you explain what you meant when you were talking about the standing wave at the end?
Oh yeah, sure. It's just saying that sine of x is equal to 1 over 2i e to the I x plus e to the, I should say sine of kx. Sine of kx is equal to 1 over 2i e to the I kx minus e to the minus I kx. And this is that sine of kx is a standing wave, but e to the I kx is a traveling wave. That's a right moving traveling wave plus a left moving traveling wave. That's e to the I kx. That's e to the minus I kx. And that makes sense because sine of kx is like the wave function you get when you hit a wall and you bounce. And this is actually quantum interference. So this is a right moving solution and this is a left moving solution. And the wave function is a sum because you have some probability to be moving to the right and some to be moving to the left. And so that's a standing wave. So in quantum mechanics, the wave function is a standing wave. And a standing wave is the sum of two traveling waves that interfere with each other. And so J sub L of Kr is equal to sine of Kr minus L pi over 2 over Kr. And so you see it's a standing wave because the sine wave is a standing wave, right? Because the sine wave is a left mover and a right mover. Except now left and right means incoming and outgoing because instead of x, I have r, the radial component. So this is equal to, then it's going to be equal to I'm going to have like an incoming wave plus an outgoing wave. So this is going to be my e to the I kr minus, and this is going to be my e to the I kr positive. Does that make sense? Did that answer your question?
So Bessel function is a standing wave.
Yeah, it totally is.
Oh, okay,
Because
so it's
it's a sine function. And so because the sine function is going to be 1 over 2i times e to the I kr minus L pi over 2 minus e to the minus I kr minus L pi over 2. Because I'm just plugging into this little formula up here. See? I'm just plugging into that formula.
okay, so it's not that after we apply the potential, it became standing wave, but even from the beginning, it was a standing wave.
Yeah, yeah.
Oh, okay.
And
Yeah,
it
that
is.
makes sense.
It's really a funny thing. Like, why is the free particle a standing wave? It actually makes sense because check it out. Let's consider the origin. In spherical coordinates, I could either have an incoming wave or an outgoing wave, right? If it's a spherical wave and it's traveling, it only has 2 ways to go, in or out. So let's consider the ingoing wave. If it's going in, if the probability current is flowing inward, that it's going to hit the origin. What's going to happen at the origin? There's nothing there. It just goes past it. So that means as it goes past the origin, it has to turn into this.
Outgoing wave.
Yeah, because if the particle is like coming in, it hits the origin, it just keeps going. Now it goes from being an incoming wave to an outgoing wave. So both of these must exist simultaneously. So for a free particle, it must, if it has some incoming solution, then it must have some outgoing solution too, because you cannot have one without the other.
Oh,
But
I
if they
see.
both exist at the same time, then you have a standing wave. Because okay, does that make sense?
Yeah,
Okay.
but that's only for spherical and not like one-dimensional or two-dimensional, right? Because it.
Well, in one dimensional too, we do the same thing. In one dimension, this is what we do. We say, what happens when I put my particle in a box? And I say, what's the eigenstate in that box? Well, you know the eigenstate, it's sine kx, right? Where k is equal to, what is it, n pi over L, right? But what the heck is sine of kx in that box? That's just the solution of the right moving plus the left moving. That's the eigenstate of a particle in a box. It's the sum of a right moving wave and a left moving wave. Why do they both are there? It's because when the particle is moving to the right, it's going to hit that wall and bounce back. So
That's right. Yeah.
you got to have some right, you got to have some left.
Okay. Yeah, that makes sense. But just one last question, because I know you probably have to go. But there's a ratio or the probability of the reflection and then the scatter. I mean, reflection and transmission, that was different, right? And if
Okay,
the reflection.
but now you're getting into a detailed question. So I want to stop this recording and start my office hour because this is being recorded. So I got to, because I can't let this recording get too big. Okay, so I'm going to stop the recording and then I'm going to shut this all down. I'm going to start back up in my office hour. And so if you have time, then you can ask me that question in the office hour. Okay.
Sure. Yeah. Thank you.